Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's hard level difficulty puzzle. And it's called Yin Yang Sum Frame Sudoku by Dying Fletchman. And here are the rules. We have normal Sudoku rules apply, which means in every cell in the grid, place a single digit from 1 through 9 such that there are no repeats in any row, column, or designated 9-cell region. We also have yin-yang shading, where we need to color the grid using two colors such that all cells of the same color are orthogonally connected, and no 2x2 area is fully one color. So this would be a valid example of a yin-yang shading. And what does it mean to be orthogonally connected for all cells? It means you can go from any cell in one region to any other cell in that region just by going through edges, all while staying within that region. So for example, to get from here to here, you just go all the way around here and then to there through edges, and you'll always be in the blue region. This is not a valid example of a valid yin-yang shading, because to get from these cells to these cells here, you have to either go through a corner or you have to go to the other region and then go through to connect. Same with this cell. This cell can't reach any of the other shaded cells by going through edges. It has to go through either a corner or it has to go through the other region before it can reach any other cell in its own region. So this is not a valid example. This is also not a valid example because we have a 2x2 area here that would be all shaded. We have two 2x2 areas, in fact, which would all be shaded. So that's not valid then as a shading. So that's an example of how yin-yang works. We have sum frame, where outside clues give the sum of the first 3 digits seen from that direction. So this is the sum of the first 3 digits seen in this direction. Okay, so that is the example. That's how sum frame works, but we don't actually have sum frame. We have colored sum frame, where each sum frame clue only sees one digit of one yin-yang color, while digits of the other color are completely meaningless for that clue. Which color corresponds to each clue must be determined. I'm so confused. Oh. Okay. Right. So, yeah, sum frame. So this is the context of what these clues are. We have colored sum frame. Sum frame itself is that the outside clue gives a sum of the first 3 digits seen from that direction. So if this were normal sum frame, the first 3 digits seen here would be 6, 8, and 9 to add up to 23. And obviously we'd have an issue with that on the other side, but we'll get to that. So basically, in normal sum frame, you would have the first 3 digits seen have to add up to that sum in outside of the grid. So the first 3 digits here would have to add up to 23. The first 3 would have to add up to 7, etc., etc. But we have colored sum frames here. So this is the actual rule set that we will use, where each sum frame clue only sees digits of one yin-yang color, while digits of the other color are completely meaningless for that clue. Which color corresponds to each clue must be determined, and each clue sees at least 3 digits of its color. Okay, so that is interesting. Note you may place colors or labels outside the grid to assist your solve. So those won't interfere with the solution checker. Okay, so that means instead of the first 3 digits, so first of all, anytime you have a sum frame rule, you're guaranteed to have 3 digits of the same color in that. Whichever color that it's seeing, it must have 3 digits that add up to that value. So, for example, say this was looking at all the blue cells. Then the sum of the first 3 blue cells would have to add up to 17. So you could have something like 2, 6, and 9. And this would be a valid sum frame. And again, it would ignore these colors. It would ignore the digits of the other color. So this could be, so this would then be, so what they say about coloring is that this looks at like the blue color. And then this would have to look at the other color, which we could, I'm going to be using blue and green. So, there is that. But basically know that every sum frame clue is a colored sum frame clue, and it basically looks at only one color. So it looks at the first 3 digits that are of the color that it's looking for specifically. So say this was looking for blue, it would be 2, 6, or 9. But say, okay, so imagine this was, can we just, I guess, color this green? Say that this 18 was looking at green. Then it could be something like 7, 8, and 3, right? And so the blues, this would be looking at blue. This would be looking at green. And so this blue would add up to 17 because it's 2, 6, and 9. It ignores the greens. And this green cell would be ignoring the blues. So it would look at 7, 8, and 3, which are the first 3 green digits, and therefore adds up to 18. So this is a possible valid example of how these colored sum frames work. And those are all the rules. If you'd like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay, the interesting one to me is, well, there's a couple of interesting ones. It's this 23-24 pair and the 7-6 and 7-6 pair here. So to add up to 23 for 3 unique digits, it can only be 6, 8, and 9. To add up to 24 for 3 unique digits, it can only be 7, 8, and 9. So that means these must be looking at the same color, and they must share the 8 and 9. So that means going from this direction, looking at that way, 23, this must see 6 and then 8, 9, and then the 24 must see 7, then 8, 9. Well, the thing is, that means in this row, you have to ignore a lot of the digits, right? Because they must be able to match 8 and 9. One sees 6, 8, 9 going one way for the first 3 digits. The other sees 7, 8, 9 in the first 3 digits of the same color. So therefore, it can only see 6, 7, 8, 9 in those. Only 6, 7, 8, 9 can be in those colors. Which means that it has to swap colors here. At least once. Maybe twice, but at least once we're swapping. Well, the same thing happens for column 1. We have a 7 looking down and a 6 looking up. 7 can only be added up by 1, 2, and 4, and 6 can only be added up by adding up 1, 2, and 3. So they must see the same set. So we have another swap of colors there. And we know this color only sees 6, 7, 8, 9 in row 1. This color sees only 1, 2, 3, 4 in column 1. So they must be looking at different sets, essentially. So 7 and 6 are looking at the same set. We're going to make it just arbitrary green. 23 and 24 are looking at the same set. So this this cannot be I guess it could be blue. We don't know which. We just know that they have to be looking at different sets, right? Because if this looked at, well, that's not necessarily the case. There could be a 5 here. Okay. Okay, that doesn't work, unfortunately. So we don't know that it's guaranteed. We do know that it sees these only see 4 cells here, and this sees only 4 cells here. Okay, what happens if we try to make them both the same set? Let's try that. So say these both looked at green. The problem with this, okay, so you can own one thing you should know about yin-yang shading, and this is I guess a developed, it's a logical proof, I guess, that we showed. But it's become a developed intuition for people who've done a lot of yin-yang shading, is you can only swap at most twice on the edge of a normal Sudoku grid if you have yin-yang shading. And the reason is, what happens if you have one shade here? Let's make it the actual 4. One shade here, one shade here, one shade here, and then a different shade here. How do you orthogonally connect the regions? Well, the problem is green has to orthogonally connect to each other, but that will break the blue region into 2 separate regions when we know they have to be one full region. So, and then what happens if you try to orthogonally connect the blue with the blue? You'll again have to break the green region up into 2 separate regions. So this is with changing of shading once, twice, 3, and 4 times. So that's why you can't have more than 2. You can't have a changing shade 3 times, because then it won't match at the end, right? If you do that. So you can only have 2 changes of shade around the edge of the grid. Okay, so actually this could work. So, okay, they could be seeing the same shading, but not in this way, right? Because you can't have 1, 6, 7, 8, 9 here, and then 1, 2, 3, 4 here. You could have the same shading if it's the very end here, right? If you have the very end here and very end here. So then this would be 7, you have 8 and 9. Oh, you can't have 7 here. Well, that foils that plot. So you could have actually had it here, because we know there's a shading change here. There's a shading change here, right? So you could have actually had it work if you could have had a 7 here. But you can't have a 7 there because 7 in the box. And right, this could have been all green if that was the case. So now since we know 7 cannot be here, this has to be all different shading. And if we tried to have 7 going here as green, well, you can't have 7 going here as green if they're both looking at green, because this would be 6, and then this cannot add up to for 3 digits, adding up to 7. Because 6 plus 1 already adds up to 7, and you can't have another 0. So that doesn't work. So then this would... You cannot have green and green there. So this is guaranteed to be green here. This has to be blue, and in this case, this would have to be green somewhere here. But then that means it swaps twice in row 1 if that's the case, and then it swaps once in column 1, so it would have to swap again to make it work. And so that doesn't work because we're swapping more than twice on the edge of a Sudoku grid for the coloring, and that's not allowed. So that's why we have to have different shadings. These looking at different shadings here, right? So 7 cannot be here. So then this must be all green. That, or maybe, yeah, we'll make these looking at green, and the other ones will make looking at blue. So this will be making looking at green. This will be blue. So 7 cannot be here. This is all blue. If we try to have we have a green here. We can swap back, but then the problem is it would have to swap back again here. So I think what it has to be then is that this has to be all blue. So it swaps once here. If we tried to have green here, we would swap again here, so that would be blue, but then this would be blue, and then it'd have to swap again, and then we'd have more than 2 swaps on the edge of the grid, which is not allowed. So these cannot be blue. These have to be all green. So then this is 6, this is 7 here, and this is an 8-9 pair this way. It cannot go green, swap to blue, and then swap back to green. So this has to be all blue here, which makes this all green there. So then the rest of the edge is all blue, because we can't swap again. So then this must be 1, 2, and 4. So that's 4, and this is 1, 2. And then this must be 3 here. So that's 3 in the corner. We celebrate because, I don't know, it actually might be fairly close to solving this. This has to be 5, 7, 8, 9. And this cannot be 8, 9 as a pair because of the 8, 9 pair in the box. So this is 5, 7 as a pair, which eliminates 5, 7 in the rest of the column. So again, this sees blue. It sees 1, 2, 3, 4, which 4, 2, and 1 adding up to blue. This has to be 1 through 5 here. And this sees 1, 2, and 3 as the first 3 digits. This must see blue because those are the only digits there. This must see blue because those are the only digits in the row. So this also sees blue, and this also sees blue here. We know we have a 2x2 area that has 3 blues, so this must be green, this must be green, and this must be green for the same reasoning. This is a 2x2 area that has 3 greens, so we have to have blue there. This 8 eliminates 8 here, so that's 9, which makes this 8. The first 3 digits here cannot have a 3, and therefore must be 1, 2, and 5 to add up to 8. So this is 1, 2, 5, which eliminates 1, 2, 5 in the rest of the row. That leaves the remaining digits as 4, 6, 7, 8, 9. This can't be 6 because of 6 in the box. This can't be 7, this can't be 8 because of 7 and 8 in the column. So this must add up to 16 here for these 3 digits. And 16 minus 3 is 13. So it's either 4, 9, 5, 8, or 6, 7. And it can't be 6, 7, can't be 5, 8. This has to be 4, 9, which eliminates 4, 9 in the rest of the row. These 3 digits add up to 20. These 3 digits add up to 19, which means these 3 digits must add up to 45, which is the whole row or whole column summed up, which is the digits 1 through 9, minus 19 minus 20. So it has to be 1, 2, and 3 to add up to 6, right? 45 minus 19 is minus 45 minus 20 is 25, minus 19 is 6. So this is 1, 2, 3, which eliminates 1, 2, and 3 in the rest of the column. This can't be 1, 2, or 3. It's 5. That eliminates 5 in the rest of the row. And this can't be 1, 2, 3, or 5, so that makes this 4, which means this can't be 4 in the rest of the row. So this adds up to 19. It has to be 6 and 9, or 7 and 8, and it can't be 7 because of 7 in the box, so this is a 6-9 pair, which forces this to be a 7-8 pair to add up to 20. Now this digit, or this sum, cannot be blue, because if it's blue, we already have a 7 or 8 there, and add 2 other digits to it, it adds up to at least 10. So this must see green. This is 6 or 9. We have the same problem. You can't, to add up to 9, 6. Oh, I guess it could be 612. Never mind. We don't know what that is. Remaining digits of box 1 are 1 through 4. And we know these add up. The first 3 digits here. Well, you can't have green because 8 already adds up to greater than 6. So this must be looking at blue. And it must be 1, 2, or 3. Which eliminates 1, 2, 3 in the rest of the column if it's green. Also, this has to be... remaining digits in box 7 are 5, 7, and 8. And, yeah, that works, I guess. Remaining digits of box 9 are 3, 4, 6, and 9. So this can't... We're looking at green here because it can't be blue. So this has to be 3 or 4 here. Which means for the rest of the greens, it has to be 3... The first 3 greens, it has to be 1, 3, 4 to add up to 8. Because it includes a 3, 4. It's either 1, 2, 5 or 1, 3, 4. So therefore, 1 has to be in the green cells in between these. So this can't be 1, it's 2, which makes this 1. For these digits, to add up to 20, 2 cannot be there in that set because 2 plus 8 and 9 at most is 19. So this must look at green. Okay. Remaining digits in... We have a 5, 7, 8 triplet, which eliminates 5, 7, 8 in the rest of the row. Also, this is... So this has to be guaranteed to be 5, which means this can't be 5 here. That means the remaining digits in row 8 are 1, 3, 4, 6, and 9. And this can't be 6 because of the 6, 7, 8 triplet in the box. So where is the 6 in row 8? It has to be here. So this is 6, but the green by itself would have to be add up to 8, and this can't be green because it's 1, 3, and 4. So this must be blue, which means green has to exit out this way. So green could go this. This cannot be 6 here. I guess we already knew that because that was 6. Okay, well, that helps that. This could be 6, 1, and 2 as blue. So that could actually work. This cannot be watching blue because 3 plus 8 and 9 only adds up to 20. So it must be looking at green here. This could be looking at blue or green. We're not sure. This is looking at green this way. But if this was green and green, the only way that would add up to 20 would be with the other 7 or 8, right? 5, 7, and 8 add up to 20. So if this is green and green, it would have to have that as green, but that's not possible. So this cannot be green and green. This must be green and blue. And if we try to have 5 here, 5, it's 6 and 9 only add up to 20. So it can't be 5, 6, and 9 because we already have a 6 in the row. That's blue. So this cannot be 5. It has to be 7 or 8. This is 5, not 8. This is 5. So the 7, 8 pair eliminates 7, 8 in the rest of the column. This is 9. That's 8. Green has to go out. So this is green. And these 3, so it must be 3 digits. It must include one of these digits. It cannot include 1. So therefore, I think all 3 of these have to be green. Right? We need a 3, 4, and 1. And this must be 7 or 8 with 9 and 3 or 4. So none of these can be 1, which means this has to be 1 here. 9 cannot be the first one seen, so this is 3, 4 as a pair, which forces this to be 9. This cannot see green, because if it's green, it has to see the same cells as this, right? So then this must be 4 here. This is 9. And this cannot be 4. It's 1, 2, or 3, which means it must be blue. So it must see 3 here. So this is 1, 2. We have 1, 2 here. No 3 here. And one of these is going to be 1 or 2. We have, and then 5 and 6 there. And the greens are 5 and 6, and the 1 or 2 is blue. But we don't know which one's which. So this is blue also. 17. Don't know. 19 could be 2, 8, 9. That is possible. So this is done. This is done. This green is done now. And we have 9. So this adds up to 11. So it could be either 3, 8 or 4, 7 here. So that still is valid there. Remaining digits of box 8. We have 2, 3, 4, 5. Okay. $18. One of these is at least green. This is 18 also. Remaining digits in box 3. We have 1, 2, 3, 5, and 8. 3 cannot be either of these. Eight has to be one of these two. In row 6. Remaining digits of column 3. We have 1, 2, 3, 4, and 7. Okay, no 4 here, though. So 1, 2, 3, and 7. Okay. This could be 9, 3, and 1 that it sees. 10. Remaining digits in box 6 are 4 through 9, and this can't be 8 or 9. This can't be 8. These can't be 4, and these can't be 7. Okay. First 3 green digits add up to 21 here? Well, 4 could be with 8 and 9 adding up to 21, but this is not 8 or 9. So this digit then can never be green. It has to be blue. So that means we have 3 blues in this 2x2 box, so this is green here. To add up a 21 then, with 5 or 7, you could have 5, 7, 9, or 6, 7, 8. And, okay, this 7 eliminates 7 here, so this is 5, which makes that 7. So, okay, we have 5, 7, 9, or 6, 7, 8. What else do we have? Uh, 10. You could have 4, 5, 4, 5, 1. Oh, this 6 also eliminates 6 in the column. That's helpful. You could still have 4, 5, 4, 5, 1. That is possible. 19. Either this is 2 with 8 and 9, or this is 3, 4 with 9 and another digit. Not too helpful there. Okay. We have 1 blue and 2 greens in column 2. This cannot be blue, because if it were blue, the remaining digits would have to be green, and we'd have a 2x2 area that's all green. So this must be green. And the other intuition or other deduced logic behind yin-yang shading is if you have one diagonal, which is the same shade, they have to have one of each shading or each color on the other diagonal. So how do you know this? Say you have these, say you have one shading here, that's one shading, and you have, obviously, this 2 of the same shading there. Well, that's a 2x2 box, which is all the same shading, which is not allowed. But what happens if we have the other shading there, right? Well, if we have the other shading, how do you orthogonally connect this to this cell without breaking apart the greens? You can't. And, right, because basically any way that you try to orthogonally connect the blue regions, the green will be necessarily divided into multiple regions, which when they're supposed to be the same regions. And if you try to do it with green, it's the same thing, right? Because it's a symmetrical shape. So if you try to orthogonally connect the greens, the blues will be into 2 separate regions, which is not allowed. So that's why we know one of these is green and one of these is blue when we have a diagonal that's the same shading. Well, we have that shape here. So this is green, green. This must be blue, which makes this green. Because again, you can't have the diagonals be the opposite shading. Obviously, it can't be the same shading because then the 2x2 box would be all the same color. But if they're the opposite shading, they can't orthogonally connect without breaking apart the other color. So this is green, green, which forces this to be blue here. And so this is 1, 2, and this is 5, 6 as a pair. Therefore, this cannot be looking at green, because if it's looking at green, it adds up to at least 9 and 5. So therefore, this is looking at blue. Let's see. 5, 9, and 3 add up to 17. So this is 8. This cannot be all green here. So if this were looking, so if we try to make this all, so the only way that blue, this can be looking at blue, is if it looks at, this is 4, and we see 5 and 9 added together, right? 4 with any other combination, even 6 and 7, or 6 and 5, or 7 and 5 does not add up to 18. 4, 6, and 7 add up to 17. So that's the most that without this 9. And for the only way you could have it is 4, 5, and 9 again. And that would force all of these to be green, but then we have a 2x2 box, which is all green here, which is not allowed. So this cannot be looking at blue. It must be looking at green here. So it's 8, 4, and then another green, which could be 6. This could be all blue, though, so that could work. So it cannot be 1 here. If this were 1, 8, 1, and 9 add up to 18, but 9 is blue here. And it cannot be 2. So it actually has to be 4 and 6 here, right, for the greens to work up. Again, for blues to work, this has to be 4, 5, and 9. You can't have... because it will always include the 5. It will not necessarily include the 9. So any of the combination, 4, 7, and 5, obviously doesn't work. And 4, 7, and 6 doesn't work for the blues. That's the reason why it looks at the greens. This can't be 1 and 9 for the other digits, and it can't be 2 and 8 for the other digits, because we already have an 8 here and a 9 here. The 9 is blue, and we've already counted the 8. So this has to be 4 and 6 to add up to 18. So that's 8, 4, and 6, which makes this green. So to add up to 7, so we know the first 3 greens in column 3 are the greens that we see here. So these can't be green, they're blue. So this would, if this were looking at greens this way, it would also add up to 18. So it can't be green, it must be blue, so it must be 9, 5, and 3 to add up to 17. That eliminates 3 in the rest of the column. So let's mark the done ones with a circle. So we have looking at blue 4, 1, 2, that works. Looking at blue 3, 1, 2, that works. Looking at blue 3, 1, 2, that works. Looking at blue 4, 1, 2, that works. Looking at green 8, 4, 6 adds up to 18. Looking at blue 9, 5, 3 add up to 17. Looking at blue 4, 6, 9 adds up to 19. Looking at blue 5, 7, 8 adds up to 20. Oops. We want to do the ones outside. Looking at... Excuse me, a frog in my throat. Whoa. Excuse me. Looking at green, 6, 9, and 8 add up to 23. Looking at green, 6, 7, 8, 9 add up to 24. This is not done. This is not done. Looking at green, well, it's not quite done there. Looking at blue, 3, 4, 9 add up to 16. Looking at blue, 1, 2, 5 add up to 8. Looking at green, 3, 1, 4 add up to 8. Okay, so this is all blue. This is green, so it has to go out here to orthogonally connect to the rest of the greens. This is, again, a diagonal here, which means this cannot be blue, so it's green. The green here can never add up to 14. It's 6, 7, 2 at minimum, which is 15. So that means this blue, this 14 must be looking at blue. We have a 2x2 box here, which is all green, which has 3 greens, so this must be blue here. To add up to 14, it could be 149 or 158. So this has to be 2 or 4 or 5 here. This then can't be blue because then that would never add up to 14, so this must be green here. We could have blue here as a 9. We could have this blue being an 8. We don't know which. So this isn't quite done. 13's not quite done. 7 we have either 5, 9 or 6, 8. Hmm. Okay. This adds up to 19. What happens if this is 4 and 7? I think that fails. If this is 4 and 7 adding up to 20, right? Because we need, again, 11 with the 9 to add up to 20. If this is 4 and 7, that forces this to be 5 and 8. But then this has to add up to 14, and it would have to be 158 to add up to 14, which it can't anymore, right? Because the 8 is here now in row 7. So this cannot be 4 and 7, which makes this 3 and 8 to add up to 20 with the 9. That makes this 7, which makes this 8. 8 eliminates 8 here, so it's 7. 3 eliminates 3 here, so it's 4. Therefore, these can't be 4. There's no 4 here either. And these can't be 3. So this still could be 1, 4, and 9. It could be 1, 5, and 8. We're not sure. Okay. 3 eliminates 3 here. This can't be 1. Let's see. What about this? Okay, this 5 eliminates 5 here. Still could be 1, 5, 4. That's blue. Okay, so this is done now. The 20 is done. 21 and the 9. It's an interesting interaction. What about 19 and 18? Um, hmm. Again, so if it was blue, you'd have to have 2, 9, and 8. And then you could have this be blue, 1, 8, and 9. Could these be opposite? Either way, this one is going to include the 9. if it was green, again, it can't be 3, 4. So if this is looking at blue, it's 2, 8, 2, 9, and 8 that it sees. Which make that 3 and 4. If it's green that it sees, it would be 4, it can't be 3, 4, 9, which adds up to 13 with 6. Ah. So if this sees blue, it sees blue as 298. I guess it could be seeing green here as 5, 6, 7. Right? Yeah. Huh. Remaining digits in row 2. Let's do that right now. We have 1, 2, 4, 5, 6, 8, 9. Ooh, that's a lot. 8 can't be here. We are guaranteed 4 and 6 are here. Okay. We don't know where the other one is. We don't know 6 is here. Never mind. We know 4 is here. 6 could be here or it could be there, right? For 9, if it looked at... Huh. Okay, for 3 digits to add up to 9, unique digits to add up to 9, you have to have 2 of the digits be from 1, 2, or 3, right? 1, 2, 6 adds up to 9, 1, 3, 5 adds up to 9, 2, 3, 4 adds up to 9. And this is the case, you actually, this is a common thing that you'll use throughout, like arrows, through like sums, a lot of things. If you ever have 3 unique digits adding up to another digit, you're guaranteed at least 2 of those digits must be from 1, 2, or 3, right? 6 can be all 3 of the digits from 1, 2, or 3 adding up to 6, right? So you have 1, 2, and 3 adding up to 6. You have 1, 2, 4 adding up to 7. That requires 1 and 2, 2 of the digits from 1 through 3. 8 can be 1, 2, 5 or 1, 3, 4, which both require 2 of the digits from 1 through 3. And 9 can be 1, 2, 6, 1, 3, 5, or 2, 3, 4. Again, requiring 3 of the digits from 1, 2, or 3. Well, in row 2, the only digits which are... We have 2 guaranteed digits that must be blue from 1, 2, and 3. Which means this has to be looking at blue cells. Because if it doesn't, then you won't have 2 digits available for the 1, 2, 3 to add up to the 9, which you have to have. So this must be blue, which makes this a 6 and this a 9. The other 1, 2 is a blue here. We don't know where it is, though. This can't be 6 here, no 6 here, no 1 here. That means we have 1 blue in these cells. And then the rest have to be green. This, well, it could be green. Blue has to go out this way. To orthogonally connect to the rest of the blues. This must be 6, 1, and 2, adding up to 9. So this has to be, cannot be 7, 6, 8. It has to be 7, 5, 9. To add up to 21 as the first 3 digits, the first 3 green digits. So the first 3 green digits are guaranteed to be in these sets. So this has to have a 5 and it has to have a 9. And we also know it already has a 4. Has to be there. So this has to be 4, 5, and 9. And this can't be 4. So this has to be 4 over here. And this must be a 5-9 pair to add up to 21 for the first digits, right? So these are all green. That makes this not 5. This is 8. This is 1 or 2. So this has to be blue. So this has to be 5, 9. This can't be 9 because of 9 in the column. So this is 5, which makes this 9. That eliminates 5 from the rest of the box. So whereas 5, this 8 eliminates 8 here. So this cannot be 8. Which means this must be 8 here. This is 1, 2, 1, 2, and 6 adding up to 9. So that's done. This is 7, 5, and 9 adding up to 21. And we couldn't have the 6, 7, 8 because this was had to be guaranteed to be 6. So that's done. We have a 2x2 box that is 3 green, so this is blue. Green has to go out, so it must go that way. This can no longer be 2, 8, 9 for the blue to add up to 8, 19. So therefore, this must be looking at green, which makes that 4, 9, and 6. So that eliminates 9 from these cells here. This is 5, 6, 7 as a triplet, which eliminates 5, 6, 7 in the rest of the row and, column and box. So this can't be 5, 6, or 7. It's 4s, can't be 4 or 5. Now it's 9. 9 eliminates 9 here, so it's 3. This can't be 4, and this can't be 5. We know the 9 here is green. So that means to add up to 14, we can no longer have 1, 4, 9. It must be 1, 5, and 8. So this is 5, 2, and 4. And this cannot be blue because we must see the first 3 blue cells. And that would force that not to. So this is green. We cannot have. So if we tried to add blue, it would guaranteed be. So this has to be 5 here. The blue would have to be 3, 6, and 7 at most, which only adds up to 16. So this cannot be looking at blue. It must be looking at green. So this is going to be 4, 9, and 6 here. So we're guaranteed at least a 6 that it sees here. 8, 6, and 4 does not add up to 18. And this is guaranteed to be 1, 2, or 3 here. So it must be 3, 7, and 8 to add up to 18. We could have all 3 greens there. So we know we have a 7 in one of these cells here because it must see the 7 before it sees the 6. And this must be one of the 6s because it must see the 6 before it sees the 7 here. So this is green. That means this can't be 3. This is 1, 2 as a pair, which eliminates 1 and 2 in the rest of the row. This can't be 2. It's 3. We already knew that because of the 2 there, but anyways. So this still could be 1, 4, and 5. So that still potentially works. And that could work also with this being green 6 and 7. So that also is possible. So 18's not quite done. 19's not quite done. We have a 5, 6 pair here. 3 eliminates 3 here. That's okay. Remaining digits of column 6 are 5 through 9. This can't be 8 because of 8 in the box. No 5, 7, or 9 here because of 5, 7, 9 in the row. This can't be 9. No 9 here. Where is the 9 in column 6? Can't be here because of 9 in the row. Nor there, nor there, nor there. So it has to be here. So this is 9. Remaining digits in row 6 are 1, 2, and 7. Okay, and 7 cannot be here because of 7 in the column. So we have a 1, 2, 7 triplet, or 1, 2 pair in row 6. So this can't be 1 or 2. It's 7, which means this can't be 7. That's 6. This can't be 6. It's 8. This can't be 6 or 8. It's 7, which eliminates 7 from either of these cells here. This is 5, 6 as a pair, which eliminates 5, 6 in the rest of the column. This can't be 6. It's 8. Remaining digits in row 3 are 1, 2, and 6. Okay. And this can't be 6 because of 6 in the column, so we have a 1, 2 pair in row 3, which eliminates 1, 2 in the rest of the row. So this is 6. Rest of... So this digit then must be a 9. Wait. That's not working. Yeah, it's 4. Sorry. I don't know where I came up with 9. Last digit in column 5 is a 4. Last digits in column 4 are 1, 2, and 3. Interesting. Okay, so this 14 is done. So we have that done. 13's looking at blues. We have a 5, 6 pair in row 5, which eliminates 5 and 6 in the rest of the row. This can't be 5 or 6. It's 7, which makes this 5, which makes that 6. So 7 has to be green, so does 6. And 5 cannot be green, because if it were, then 8, 3, and 5 would have to add up to 18, which it doesn't. It adds up to 16. So this is 7. It could still be... Okay, so... It could still be green? No. 7 eliminates 7 here. Therefore, this is 1 and 2. Here. We have a 1, 2, 3 here. If this were counting green, it would have to be 7 with 1 and 2, but one of the 1 or 2 is in blue, so it can't add up that way. So this must add up the blues also. Interesting. Without 9 or 8, and one of the 5 6s, and let's say this was not blue, that means what would this add up to at most? Well, 6, 4, and 3 does work, but if this has to be 1 or 2 here, because it can't be 3. So if blue is not... If 8 is not blue, then this doesn't add up to 13. Because it's just too... Yeah, there's just not enough... it just doesn't add up, right? We have 7 and 9 already green. We have another 5, 6 as a green. So if 8 is also green, that means you have at most 3, 4, and 6, but then this can't be 3 as the first digit. Or 4 or 6, obviously. So this is 1, 2 as a pair, which means this can't be 1 or 2. It's 7. So this has to be blue here. So we have 1, 8, and 4 adding up to 13, or 2, 8, and 3 adding up to 14. If we have 1, 8, and 4 adding up to 13, that would mean these are green to add up. But then you'd have 2, 4, at minimum, 4 and 8, which doesn't add up to 10. So this cannot be 1 and 4, it must be 2 and 3 here. So this is 2, which means this can't be 2. This can't be 2. 3, 4, and 3 would add up to 10, but that doesn't work. So we cannot include the 8 here. So this must be the first 3 digits here, and it must be 1, 4, and 5. So this is 1, 4, and 5, which makes this 3. 1 eliminates 1 here, so it's 2, which makes this 1, which makes this not 1 or 3, it's 2, which eliminates 2 here, so it's 1 and 2, which eliminates 2 here, so that's 1, which makes this 2, which makes that 1, and 2, which makes that 1. So these are all blue. This can't be blue because of the 2 by 2 area has 3 blues, so this is green. This 2 by 2 area has 3 greens, so this is blue. This is a diagonal of blues, so this must be blue here. Green has to go out, so it must connect to there. Three blues here, so this cannot be blue here, so that's green. Blue has to go connect out, so that's blue. This has to be blue to add up to 13, so this is 2, 3, and 8, which means this is a 2x2 area that has 3 blues, and so is this, so these must be green. And this is the yin-yang shading, and we fill out the rest of the digits. This can't be 2, that's 1, which makes this 2. This can't be 1 or 2, it's 3, this can't be 5, so this is 6, which eliminates 5 here, so that's 6 and 5. Well done! Hope you had fun, and don't forget to keep fletching. Yeah, it was good. It was really nice. Really well constructed, I felt. Again, these are all done. Now let's look at the 13. 2, 3, and 8 add up to 13. So that's done. 1, 4, and 5 add up to 10. So that's done. 4, 9, and 6 add up to 19. 8, 3, and 7 add up to 18. And those are all that's all done then. Very nice shading too, actually. It's very cool. Interesting little pattern for it. Anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.